Hello everyone, my name is Renshi Hong, and welcome to my presentation of our paper by Laurent Pottier, Michel Buffa, and myself. From Diagram to Code, a web-based interactive graph editor for Faust DSP design and code generation. I'm going to show you a tool that I made called JSPatcher, which can be used to design Faust DSPs in a straightforward way, just in a web browser. I'm sorry if you already heard this from the programmable audio workshop a week ago, but you will see one more thing at the end of this presentation. First of all, I want to talk about why I choose Faust as the language to use in our DSP design workflow. One reason is that if your DSP is already written in Faust, it means that the DSP can be quickly exported to a large variety of platforms. The other reason, which is the most important one, is that everything in Faust can be considered as an audio stream, and these streams are functional. So the way we design Faust DSP is just like connecting audio cables between different inputs and outputs of analog audio devices. This reason actually brings us to the main purpose of this language. In fact, Faust language is designed to be an interpreter to calculate from an audio graph to machine-readable low-level codes. So it provides a very efficient solution to let us to be able to describe complex audio graphs into plain text. Then it's up to the compiler to make these texts understandable by machines. This process is called block diagram algebra. So Faust is a powerful language that takes care of both human users and machines. Its text-based form might be a sweet point, but it is still not easy to learn. To write in Faust, you need to learn how to manually translate a graph into the code, to flatten these cables and connections into plain text. And this needs sometimes hard work, especially for beginners. For example, without compilation, we don't always know how much inputs and outputs these modules actually have if they are imported from a library. Fortunately, a bunch of tools are provided to make the coding experience much better. I wrote last year with Graham's colleagues the new Faust IDE, in which users can watch the block diagram of the code written just in time, or they can test it and visualize the signals directly in the web browser. After having Faust IDE, I think we are ready to go further. As Faust code is already a representation of an audio graph, why not generate it from a graph automatically, so that we can design a DSP without coding? Here is what I imagined. We build a graph in the browser, it generates the corresponding code for you, and you can test it directly just in time. The approach is already used by Gen, which is a graph-to-code generator to build sample-accurate DSP in Max. Actually, I used Gen quite a lot when making projects in Max, so I think it will be nice if our Faust graph-to-code generator shares the same behavior as Gen, to facilitate Gen users to switch to Faust. Here are 4 behaviors in Gen that I implemented in the Faust graph-to-code generator. First, a graph connected with these boxes is called a patcher. Each box in the patcher represents a function that takes some arguments or inlets. Note that a predefined argument will replace an inlet into a constant value. Second, when Gen analyzes the graph, it will iterate the outputs and search the connections above. So without any generation, its inlets will be the default value 0. Then multiple connections into the same inlet will be merged and added together. If you need to introduce a loop into the graph, it should be delayed by at least one sample by the history operator, like Faust's recursive composition with tilde. Gen also supports 2 types of subprocess. You can use a code box to write Gen's code, or put a subpatcher. These subprocesses are especially useful when you want to reuse it in different situations. So with these basics, how do we generate the false code from a graph? Let's take a look at some examples. For these functions, we know that all of them can be formed as one identifier as a result equals the function's name with parentheses and arguments separated by commas. Here, ma.sr has no input, so no arguments. Sine has one input and add has two inputs. Then, for OSCRQ, which is an oscillator based on 2D vector rotation, it has one input and two outputs. So we need to give an identifier for each of these outputs. Here are some more examples to show how arguments and connections affect the code. With the graph's inputs, they have their index and identifier, and can be composed easily as function arguments. In addition to Jan's argument usage, you can use an underscore as a placeholder that allows you to omit an argument declaration and leave it as an input. For example, en.ar, which is attack release envelope, needs three inputs: the attack time, the release time, and the trigger signal. Here, we fixed the release time, and the first input goes to the attack time, the second input goes to the trigger signal. You can also put a function name instead of the underscore or numbers to use it as an argument. Also, we know that for some pattern matching related false functions, the number of I/O is variable. In these cases, we need to declare explicitly the number of I/O of the function to use it in the patcher. Here, bus 5 should have 6 inputs and 5 outputs, where the number 5 occupied already the first input, so it leaves 5 available inputs. Generating a graph with a loop is one of the trickiest things in this system. We know that in Faust, the recursive composition operator tilde should be used in a loop so that we can identify easily every loop in the graph. Jan Oglari proposed to put all these loops outside of the rest of the graph to facilitate the cable management. So in this case, the main graph has 2 inputs and 2 outputs, where one pair of them are used to build the loop. Here is an example of code block subprocess, where you can have some Faust DSP code in a subprocess connected in the main graph. I use here the environment keyword to ensure that the subprocess is in a closure, then just export the process function. After each change of the code, I evaluate the code to get information about the number of inputs and outputs so that the outer graph can connect it properly with it. I also implemented the subpatcher that will be transformed into a width expression in which you can use identifiers that are defined at the parent patcher. There's something that is quite special in Faust language, the iterators. More precisely, par, sec, sum, and prod, these 4 functions. They accept a subprocess with a variable that changes for each iteration. So this means the box that presents the iterator should have a corresponding number of outputs with an additional variable output that attached to the subprocess. Here's how it looks like. Part 3 means 3 parallel processes as the outputs. So we have 3 outlets with an additional one that will attach to our subprocess. In this 4th outlet, the variable iterates starting from 0. In the subprocess, we are going to have oscillators with 3 different frequencies. The result of the process is going to the inlet of this par to complete the subprocess. In the generated code, the subprocess is transformed to a lambda function. For some polyphonic synthesizers, we may need to declare a general effect for all the voices. In this case, we can use the effect box to connect a subprocess that will be used as the effect. The last thing we need in this system is some UI components. Just as the declaration in Faust, we can put some sliders, groups, and so on with its properties. The corresponding UI can also be generated in the web page. Now we are going to build a working example that uses our Faust patcher to make sound. We will start by creating a Faust patcher, which is a phasor. Our first input is the frequency, and we need to divide it by the sample rate and get the period. Then we connect this value to an integrator with a loop, so that we will have a value that increments for each step. We need to put an F mod in this loop, so that this value can be wrapped between 0 and 1. Now we just have to connect this result to our output, so that we can have the full code. After some graphical adjustment, we can save this patcher into the name phasor.dsp path. Then we can use this phasor to build our first sine wave generator. As this generator will be a MIDI polyphonic instrument, we will have some parameters like freq, gate, and gain. Here we are creating a Faust subpatcher with an argument which is the file name of our phasor patcher. We will just multiply this output of our phasor patcher by 2π. Then we send this value to sine, and we can get a sine wave between -1 and 1. Then we are going to multiply this result by gate and gain. We can also put an envelope after the gate, so it can sound better. Now we connect the output, and we will have the generated code. We save it as midi.dsp path. Now we are creating a JS patcher instead of a Faust one, because in JS patcher we can actually test the Faust patchers with MIDI inputs and audio outputs. If we don't have a MIDI keyboard, we can also use this on-screen keyboard to generate MIDI events for Faust. Here we load our Faust patcher and connect MIDI inputs onto it. Make sure a voice number is added to have it on polyphonic mode. Then we can use a gain controller to visualize if it actually works. Now we can connect it to our audio output. After tested this DSP, we are going to try some Faust UI. We are putting an Faust DSP to measure the RMS value and display it. We are importing a Faust patcher that we prepared. It will measure the root mean square of 400 recent samples. Now we are putting a Faust UI object that will receive the Faust node and generate the corresponding UI for it. The one more thing I would like to demonstrate is that from Max, we can actually pick a gem patcher, copy and paste it into a gem patcher from our environment. It will also be compiled to Faust and runnable in the same way. Note that this feature is partially implemented because there are still a lot of differences between the two languages and environments, like buffer manipulation and file management. Here we are picking a bit crusher from Max Gen's examples, and we are going to test it with our sine wave generator. To make the UI usable, we may need to modify the min and max value of parameters. And we can add some visualizations like oscilloscope or spectroscope to visualize our signal. So what I demonstrated, the Faust patcher in JSPatcher, is only the first important feature that we implemented in this project. The project is open source on GitHub, but still on a very early stage, so you won't find any documentations yet, but they will be coming. We're going to make the JSPatcher to support not only Faust, but also many WebAssembly compatible languages or tools, so that it could be a place for artists or programmers to experiment their ideas with graph and codes. Back to Faust, I think the web environment shows many potentials that we haven't explored yet. For example, we can have multiple Faust DSP instances in different audio contexts with different sample rates. Or we can just use Faust DSP as a normal function or non-audio usage. This brings us the possibilities to use Faust to process like FFT data or even videos. These should be interesting to be part of JSPatcher. Yeah, so this is the end of my presentation, and thank you very much for your listening.